So Haley's theorem said that given n convex sets in RD, K1 to Kn, if n is greater or equal to d plus 1, and if every d plus 1 of the sets has a point in common, then all of them has a point. So here is the proof. Okay, so proof. It is enough to prove that if every n minus 1 of the sets have point in common, then all of them have. Because then we can continue by induction. Well, I mean that if that for n greater than d plus 1, if every n minus 1 of the sets have a point in common, then all of them have a point in common.
n greater or equal
to d plus 1. So if n is equal to d plus 1, there is nothing to prove. And if n is, and it's enough to prove that if every n minus 1 of them has a point in common, then every n of them has a point in common. And now let's denote, so let's assume that, and let's assume that, and that xm, no, not xm, let's call it ym be a point which belong to K1 intersect K2 intersect Km omitted intersect Km plus 1 intersect Km. Okay, so for every n minus 1 of the sets, we can find a point which belong to them. So we make this notation that Ym is a point which belongs to K1, to K2, to Km minus 1, Km plus 1, and so on up to Kn. This is the note. Omission. Okay. So we have these n points, y1. Okay, so now we look at the point y1 up to yn. And we know that n is bigger than d plus 1. So therefore, by Radon's theorem, we can find S and T in 1 up to n, so that S intersect T is empty, and the convex hull of yi, I belong to S, intersect the convex hull of yi, I belong to T, is not empty. So let's assume that Z belong to this convex hull. So point Z belongs to this intersection of these two convex hulls. And now we can ask ourselves to which of the original sets this Z belongs. So, okay, so the fact that Z belongs to the convex hull of yi, I belong to S. So Z belongs to the convex hull of II, so that I belong to S. What does it mean? Now, this means that Z, each yi, for each yi, I belong to S, and J does not belong to S, yi is included in Kj. Because the index of yi is the index of the set we omitted. And if we look at the index which does not belong to S at all, it was not omitted for any of the yi's. And therefore each of the yi's belong to Kj, if J is not in S, and therefore the convex hull belongs to Kj. So the convex hull of yi, I belong to S is included in all the convex sets which are not in S. and also Z belong to the convex hull of all Yj, J belong to T. And by the same argument, this means that Z belong to KL for every L which does not belong to T. So, in conclusion, Z belong to Kj for every J which is not in S, and Z belong to KL for every L which is not in T, but S and T are disjoint. So, I'm sorry, S and T...
Partition.
What? It's a partition even, but in any case, every element does not belong either to S or to T, because they are disjoint. S and T are disjoint, every element from 1 up to n does not belong to one of them. And this because S intersect T is empty, Z belong to Ki for every I1. So this is the end of the proof of Haley's theorem. So it's a very nice proof. You can so it's a very nice proof. So geometrically, if you have, let's say in the plane, if you have 4 sets in the plane, and we have Z1, I'm sorry, Y1, Y2, Y3, and Y4. So Y1 belongs to K2, K3, K4, Y2 belongs to K1, K2, and so on. So we look at this Radon partition, and this point inside must belong to all the sets. Okay, so this is the proof of Haley's theorem. Very nice. So Haley's proof was different. Haley's proof was based on another basic geometric property of convex set, which is the separation property. It's also not so difficult. He assumed to the contrary that say Kn does not intersect the intersection of K1 up to Kn-1, separate them by hyperplane, and look at the intersection of all the sets with this hyperplane and reduce it to one lower dimension. So this was Haley's argument. Okay, now let's try to see what is the topological content of Radon theorem and of Haley's theorem. So where is Radon theorem? Here is Radon theorem. So let's leave them and let's see if they have some topological one. Maybe I'll mention a third theorem. There is a third theorem which is quite. It will play a role later. So this is Kara-Teodori theorem. Kara-Teodori theorem. It says the following: if S is a set of points in Rd, and let's say the size of S is bigger than d plus 1, and X belongs to the convex hull of S, then there is R, a subset R of S, so that the size of R is at most d plus 1, and X belongs to the convex hull of So this is Kara-Teodori theorem. If you have a point in the convex hull of some set of points S in Rd, a set of points with more than d plus 1 points, and it's already in the convex hull of d plus 1 of the points. In the plane, if you have a point in the convex hull of some large set, it is already in the convex hull of 3 of the points. You can see that it's also best possible, you know, if you, let's say we have many points, and we have points in the convex hull. So the theorem says that this point in the convex hull is already in the convex hull of some triangle. Of course, we cannot hope for better, because if we take only convex hull of pairs of points, they are very sparse in the plane. So, but okay. So this is Kara-Teodori theorem.
Why was he interested in that?
Kara-Teodori. I'm not sure much.
He was an analyst. Yeah.
I don't know. I mean, now, in some sense, Kara-Teodori theorem is dual to Haley's theorem. In some sense, but how do you prove Kara-Teodori theorem? So the proof is very easy. Let me tell you the proof. Just in one line, you write so x is the convex hull, some alpha I. Let's say that S is x1 to xn. Of course, you know, if you have a point in the convex hull of an infinite set, by definition it's in the convex hull of some finite subset. Now let's say that x is equal to some alpha I xi I from 1 up to m, and all the alpha I are positive. Let's say that we have a point which is in the convex hull of m points, and let's say that m is bigger than d plus 1.
If you want some of the alpha i's to 1,
What?
you want some of the alpha i's to be...
Yeah. So let's say we have a convex combination of x as a convex combination of m points, and m is bigger than d plus 1.
Alpha is strictly bigger than...
Yeah, let's assume that, because I take here m, which is smaller than n, so if there is some points with zero coefficient, we just disregard it. Now, if m is d plus 1, then we are already, maybe I should, ji, you know, this is not so original. Okay, so we have a convex combination. What I want to say, if we have a convex combination, and it's involved more than n plus 1 point, more than d plus 1 points, I can reduce one of the points. How do I do this? I look at the affine dependency. So if m is bigger than d plus 1, there is some beta I xi which is 0, and some of beta I is 0. This is affine dependency as before. And now I take this affine dependency and add it to this sum. So if I take this affine dependency and add it sometimes small s, and add it to this representation, then the sum will not change because I added 0, and the sum of the coefficient will also be 1. So if all these numbers are positive, as long as s is very small, it will still be positive. At some point, one of the coefficients will become 0, and then I can throw it away. So this means that every time I have convex combination with more than d plus point, I can by adding affine dependency, I can reduce the number of points. Okay, so this is the proof of Carter-Doris. Okay, now we want to talk about the topological content of these theorems. So maybe I'll ask you, let's look at Radon theorem. Does Radon theorem remind you of any, if the questions or?
What's the beta I? I missed something.
No, if you have more than n d plus 1 points, then the points are affinely dependent. And this is the affine dependency between them. And once you have affine dependency, you can add the affine dependency to the convex combination. And if you add it with, if you start with small weight, then you can cause one of the coefficient to vary.
Maybe it's worthwhile to mention that the beta i's are not all 0.
The what?
The
Yeah.
beta i's.
Okay, so this is a Carter-Doris theorem, and okay, what is the topological content? Does Radon theorem reminds you some topological statement?
If you don't remember, you fail
What?
the course.
What?
If you don't remember, you fail the course.
No. I mean, it's not. That's. So one way to look at the Radon. No, let's say we look at. Of course, Radon theorem is not true for 3 points in the plane. You have 3 points. Yeah, there's no 2 that the convex are. But now, let's say we take these 3 points and we project them linearly to the line. And now the Radon theorem tell you that here's something correct. This point now is between these 2 points. So we cannot maintain this nice position when we project it to one low dimension. Are you familiar with some topological theorem with sort of similar flavor? Okay.
Similar flavor to what?
To this statement.
Say it again, what?
we take the vertices of the triangles and we project them on the line, and somehow
There is less room.
there is less room, so this point now becomes the convex hull of these 2 points. Okay, so I tell you what is
Some kind of fixed point forward line?
Yeah, it is.
Nielsen something.
yeah, so I think I will show you what so let me run some very basic theorems. Many application is so-called Borsuk-Ulam theorem. It says that if f from Sn to Rn is continuous, here Sn is the unit sphere, so Sn is all the point x in Rd plus 1, whose norm is 1. Then there exists y in Sn, so the f of y is equal to f of minus.
You should have invited for June.
Okay. Yeah. So this is the Borsuk-Ulam theorem. It says that if we have any continuous map from if we have a continuous map, say from S1 to R1, then for every such map there are 2 antipodal points which are mapped to the same point. Okay, so this is an important theorem. It has many applications. Okay, now let's see how it's related to a Ladron theorem. So I'll show you one relation. So let's say a consequence of Borsuk theorem. Let's say K is a smooth convex set, smooth convex body in Rd plus 1. Let's say smooth, strictly convex. Convex body in Rd plus 1. So what does it mean? Convex body means that it's convex set and compact. Convex body means compact convex set. Smooth means that at any point in the boundary there's only one supporting hyperplane. And strictly convex means that if you have 2 points in the boundary, then the line segment, the interior of the line segment between them is in the interior of the set. So you don't have straight, I don't know if we need even strictly convex, but let's assume that. Okay, so we have a kind of, okay, so now I claim the following.
Smooth means that you have a well-defined tangent plane.
Yeah, we have a unique, well-defined tangent plane on each point. Yeah, and I think this is all you need actually. Each direction. Okay. And now the theorem says that if f from the boundary of K to Rd is continuous, then there exist x and y in the boundary of K. X and y belong to 2 supporting, 2 parallel supporting hyperplane. And f of x is equal to f of y. So this is Borsuk-Ulam theorem. Now we have a convex set like this, which is not a sphere, and we have a continuous map from the boundary to the line. And the extension of Borsuk-Ulam theorem said that we can find some direction where the 2 hyperplanes, the intersection of the 2 hyperplanes in this direction, which are these points x and y, they map to the same point. So this looks much more general than Borsuk-Ulam theorem, but actually it's the same theorem, because we can define a map from for any direction. We can now define it. Let's say this is a map F. We can define a map G from Sn to Rn, and for any direction, any vector in Sn corresponds to some direction. In this direction, we look at the point in the boundary of K, and we define G to be the value of this point. So if we have a smooth convex body f, we can move from any such function to a function from Sn to Rn. And then we can apply Borsuk-Ulam theorem, and we get this result, right? Okay, so this, although it looks more general, it's essentially this. It don't. Okay, but now we can move to a limit. You know, smooth convex bodies, they approximate any convex set. And now we have a consequence. If P is a polytope in Rb plus 1, so a polytope is the convex out of a finite set of points, and F is a function from the vertices of P to Rd, and now there's no point to talk about continuous because this is a discrete set. Then there exists, like before, there exists two supporting hyperplanes, and two supporting parallel hyperplanes, and say H1 and H2, and we have n 2 points, x and y. X belong to H1 intersect P, and y belong to H2 intersect P, and f of x is equal to f of x. So this is, okay, this is a statement which is more general. You see, this statement, we talked about smooth convex bodies, but by moving to a limit, it works for any convex body, even if it's not smooth. And for any convex body, it may be the case that x and y are not uniquely determined by the hyperplane. Okay, but this is still works. So by limiting.
But F is a map. Just
Now here
from
F is a map
vertices.
from the vertices. So
You extend it affine. What do you mean?
right, yeah. So you extend it affine.
So to
So-
say F, the extension, F tilde or something.
Well, you know the way
The x and y are not in
right.
P.
Yeah, you are right. You are right. F is vertices, and you extend it affine. Actually, you don't even to extend it. You can extend it affinely. You can also extend it continuously, but even continuously. But the way the argument, the way it works here, it's affinely. But the truth is that you can extend it even continuously. And okay, so this theorem is a consequence of this theorem by moving to a limit. I didn't show you the argument, but you can reconstruct it yourself. Okay. And now, if this polytope happens to be the simplex, so if you have the simplex, so now your polytope is the simplex. Say in R suite, the tetrahedron. So here is the simplex in R suite. Then, what does it mean to have these two supporting hyperplanes? They correspond to disjoint faces of the simplex, and this precisely corresponds to partition of the vertices. So if P is a simplex, this is Radon zero. Okay, so this is a okay. So if you have a simplex, so let's look at the situation, say from R2 to R1. We have a let's say we have a map from the vertices of the triangle to R1. We have a map. We extend it affinely, and then what the theorem says? It says that we can find two parallel hyperplanes. Let's say this, and 2 points. Say this point and this point that are mapped to the same point. So this means that the convex, in the images, the convex out of these 2 points intersect the convex out of this one. So this Borsuk-Ulam theorem tells you something about polytopes. And if you specify it to simplexes, you get Radon theorem. Of course, this is not the easiest proof of Radon theorem. And also, this proof.
No, I still lost. Can you repeat why
Yeah.
this implies Radon? Why this is the same as Radon?
Because
Radon was like a trigger.
No, yeah, I don't say it's.
But what is, I don't understand, why the fact that you map?
Okay, let's see the statement for the tetrahedron. We have here, this is the tetrahedron. This is the D plus 1, the simplex in R2. Now we map the vertices of the tetrahedron to R2. So what does it mean? It means, so this is X, this is 1, 2, 3, 4. So now in R2 we have 4 points. X1, X2, X3, X1, X2, X3, X4. Now, our more general theorem tells us that we can find two hyperplanes, two parallel hyperplanes, and points in the intersection of these two parallel hyperplanes with the boundary, so that the image of this point go to the same point. So for example, one possibility is that we have one parallel hyperplane which contains this edge and another parallel hyperplane which contains this edge. If two parallel hyperplanes, they cannot contain the same vertex. So they must correspond to a partition of the vertices. So we have a point here. So the point here is in the convex hull of 1 and 3. So we have a point here, and we have a point here, which is in the convex hull of 2 and 4, which are mapped to the same point. So this is what Radon theorem tells us. So in general, if you have two hyperplanes, either one of them touch an edge of the. I should have brought a tetrahedron. But if you look at the tetrahedron and you look at a hyperplane in two parallel direction, then for every partition of the vertices, you can find such two hyperplanes. In any case, any of these two hyperplanes, the intersection with the vertices is a disjoint set of vertices. So this is why this statement, this topological statement, implies Radon theorem. I should say that first of all, this is not the easiest proof of Radon theorem, as you, because I didn't prove to you Borsuk-Ulam theorem, which is a fairly, it's a second level. It's fairly difficult. You need some cohomology ring. I mean, it's not. It's more difficult. And also, for example, for Borsuk-Ulam theorem, there is no algorithmic version. In fact, it's believed that to find such X is computationally difficult. And therefore, this does not give you an algorithm. And as a matter of fact, now that I think about it, for this theorem, for general polytopes, I don't know if there is a algorithmic way to efficiently find such polytopes. So this is interesting. Anyway, so this is the connection between Radon theorem and this one connection between Radon theorem and topology. And this connection, or some variants of it, are quite important in what we will study, because it turns out that if you look at some extension of Radon theorem, the only way we know to prove them is using this topology. So for this, this is really, looks almost silly to use Borsuk-Ulam theorem to prove Radon theorem, but for some extension of Radon theorem, the only tools we know how to prove are the topological tools. Okay, so this is the topological content of Radon theorem. What about Heli theorem? So, and perhaps one more word about Radon theorem to see that there is some subtlety here. Suppose we ask about Radon theorem on a tree. So a tree, when we think about this topological space, a tree is a one-dimensional contractible space. So it's very much like the real line. But on the tree, Radon theorem is not true for the same parameter. So even if we have this simple tree, we can have 3 points. We have a notion of convex hull. And we have these 3 points, and there is no Radon partition. And actually, if we talk about higher dimension, where a nice analog of Rn are buildings that we encountered in the previous semester, I don't know what is the right Radon number for building. Maybe it's one more, maybe it's D plus 3 instead of D plus 2. But I'm not sure about it. It's sort of interesting.
What is for trees?
I think for trees, it's I think if you have 4 points, I think you are in good shape, right? Because it looked to me that 4 points are always sufficient, but I'm not. Yeah, so for example, let's take this tree. Let's say we have 4 points. 1, 2, 3, 4. If we have 4 points, then you see now the convex side of these two intersects the convex side of these two. So I think 4 points always works for trees. And I don't know what situation for building it may. Okay. Anyway, now what about Haley's theorem? So does Haley's theorem look to you having some topological content? Does it remind something from topology? Those of you. So, and in particular, Haley's theorem talks about convex sets. So convex sets are very nice sets from the point of view of topology because all the convex sets are contractible. So convex sets are homotopically, they behave like points. So is Haley's theorem true if we just replace convex sets by contractible sets? This is Haley.
So it's like the intersection property.
Oh, okay. So what is the intersection property?
I mean, just like the definition of finite intersection property, it just looks.
Yeah. So one thing that Haley himself did in 1930. So Haley proved a topological version of Haley's theorem. And what Haley proved, I think around 1930, is that if K1 up to Kn are, say, compact sets in R and D, and if each Ki is, say, contractible, or if you want, each Ki is homomorphic to, but it's not enough that each one of them. So the problem is, it's not enough to assume that the sets are contractible. And why it's not enough? Because for convex sets, we have some extra property. And the property, the crucial property of convex set is the intersection of 2 convex sets or 3 convex sets is also convex. This is, of course, not true for contractible sets. You know, this set is contractible and this set is contractible, but the intersection is not contractible. So if each Ki is contractible and each a non-empty intersection of the Ki's is contractible, then the analog, the Haley's theorem climbs.
So I guess n must be bigger than b plus 1 or something?
Complex sets, n bigger than d plus 1, bigger or equal. So we have d plus 1 and more contractible sets. If all the non-empty intersections are contractible, and if every d plus 1 of them have non-empty intersection, then all of them have non-empty intersection. So this is Haley's topological theorem. And it's quite remarkable that he proved such a theorem in 1930, and because this theorem is related to much more, this theorem is related to a very important technique in algebraic topology that was introduced several decades later, and it's known under the name of the nerve theorem. And the nerve theorems were introduced by Jean Leray and by other mathematicians for various purposes in algebraic topology, including there were several notions of homology, like check homology and the simplicial homology and singular homology, and the early application of the nerve lemma was to show that the check homology coincide with the singular homology. And the nerve lemma was also, although you don't need spectral sequences to prove the nerve lemma, it was one of the first appearances of the notion of spectral sequences, Leray spectral sequences, which is very important method in topology. And what does the nerve lemma tells you? So if you have a space, let's say X is a space, and you can cover it by some other sets. So let's say X is a space, topological space. You cover X by Y1 up to Yn, and each again you have the same property. Each non-empty intersection of the Yi's is say contractible. Okay. So such a covering is called in topology a good covering. Good covering. Now, why is it good? The reason it's good is that the intersections of these Yi's give you a complete picture on the topology of the space X. So, and the theorems which give you this connection are called nerve theorems. There are various variants of nerve theorems according to whether you talk about homotopy or homology. So there are various variants, but they all, I'll just state one variant. This is the nerve theorem. But before I'll state the theorem, I'll tell you what is the nerve. If Y1 up to Yn are sets, the nerve of this system of sets, the nerve N, is an abstract simplicial complex on 1 up to N. So it's an abstract simplicial complex on the points 1 up to N, with the property that S belong a subset. Okay, so we already wrote that this is N with square bracket. S in N for S in N, S belong to the complex, to the nerve, if and only if the intersection of Yi, I belong to S, is not N. So the nerve is a simplicial complex that record the intersection, which sets have non-empty intersection and which sets don't have non-empty intersection. So this is called the nerve. So for example, if we have, say, 1, 2, 3, 4, we have these four sets, then the nerve will have 4 vertices, say Y1, Y2, Y3, Y4. Then we have 1, 2, 3. So in this case, the nerve will be a graph with okay, and the nerve theorem says that the nerve N, so if Y1 up to Yn is a good cover of X, and you know, maybe you have to assume some nicety of X, I don't know, they're not too wild topologically, then the nerve is homotopically equivalent. So equivalent to X. So this is a very useful theorem because it says if you want to understand the topology of a space, all you need is to find a good cover. And then from the combinatorics of the intersections, you can recover the topology of the space. Okay, so this is the nerve theorem, and now from the nerve theorem, of course the nerve theorem was proved several decades after Haley, so in some sense Haley anticipated this development, but once you know the Nerf theorem, Haley's theorem follows immediately, because if there was a counterexample to Haley's theorem, then the convex sets which give this counterexample, their nerve will be the simplicial complex, which is the boundary of a simplex in higher dimension. And the boundary of the simplex in higher dimension is homomorphic to a higher dimensional sphere, to Sn or even higher dimensional. And you cannot find a subset of Rn which is homotopically the same as an n-dimensional sphere or a sphere of higher dimension. So this is again a proof of Haley's theorem using harder topological notions. It's applied in more general context. And this time the proof does apply also to convex sets in any, also on a tree or in a building. So this time the analog of Haley's theorem works for buildings or for trees, because we only use the fact that if you have a subset of Rn, you cannot have, for example, n-dimensional non-trivial homology. And this is true for any of these contractible n-dimensional space. Okay, so this is Haley's theorem and its topological counterpart, the Nerf theorem and Radon theorem, and its topological counterpart, which is Borsuk-Ulam theorem. And you can ask, what is the topological Carter-Odori theorem? And you know, we ask it now. You can ask, do you know what is the Carter-Odori? And here the collective view.
I was thinking that ich muss vielleicht Deutsch unterhalten und Sie fragen, was die Leute wissen.
Okay.
בגלל שבאנגלית אין הבדל בין יחיד לרבים, בגרמנית יש.
Okay, but in this case, even the plural you, so many of us thought for quite a while what is the right topological analog of Carter-Odori theorem, and we don't have a clue. So this
There is
is
another question. When you talk about topology, where you can you in plural, that you can algebraize it and ask it in algebraic geometry, which is an algebraic version of your algebraic topology.
This I don't know. I mean, the Nerf theorem, you can have versions for homotopy, versions for homology. It works in all these versions. But when you move to algebraic geometry, I am not familiar with any.
I don't know either.
I don't think any of us move this type of theorems in this direction. Okay, so now let me tell you the next theorem, which is the colorful Carter-Odori theorem. This is a nice theorem, and this will be very useful for us. So here is a theorem, colorful Carter-Odori. It was proved by Barani. So the following. Suppose that X belongs to the convex hull of X belongs to the convex hull of Z1, intersection the convex hull of Z2, so intersection of the convex hull of ZD plus 1. So you have not one set, but D plus 1 sets in RD. So everything in RD. So you have D plus 1 sets in RD, and X belongs to the convex hull of each one of them. Then there exists Z1 in Z1, Z2 in Z2, up to ZD plus 1 in ZD plus 1, such that X belongs to the convex hull of Z1 to Z2. This is the colorful Carter-Odori theorem. Okay, so this is a more general. Why is this more general than Carter-Odori theorem?
Take the same set.
Yeah, if you take the same set D plus 1 times, then you get Carter-Odori theorem. So this is more general. It's a very nice theorem. And for example, for this theorem, we don't know an efficient algorithm to prove. It's a big open, I don't know, big. It's a moderate, it's a notable open problem. The question is there a polynomial algorithm to find such a z1 to z2 plus 1? Because for Carl-Dodori theorem, it's simple linear algebra. Just by affine dependency, we can eliminate. Yes.
I don't understand what this says. The intersection is convex sets is a convex set.
So x belongs to the convex hull of z1, the convex hull of z2, and so on up to the convex hull of z2 plus 1.
Okay, I see. It's not a convex hull. It's not a convex hull. It's in the z. Never mind. It's got it. Sorry.
It's okay? Okay. And it's an open problem to find an algorithm. So I'll show you the proof. The proof gives an algorithm, but it's not known that this algorithm is efficient. And for all we know, it can be it is possible that there's no efficient algorithm for this theorem. And this theorem will be crucial for the next steps, which bring us to the overlapping property, and we will do it next time.